today testing a Blue Yeti microphone, which I hope is gonna sound good. I don't know. I tested it earlier, but not with the stream, and it seemed okay. We'll see if it catches a lot of background noise. We'll see. I might just switch to that as well. I think using the headset was good, and actually it's good because I think you get the best quality from the microphone. That is because it's just in front of your mouth. The only problem is I have the whole thing here, you know, the ears covered all the time, and at some point, I mean, after 2 years of doing this, it's just you end up tired. I mean, don't get me wrong, it's good if you're kind of video conferencing a lot and you have to listen a lot of, then talk, and just on the go is also great to pair it to the phone. But I think for the streams, maybe the Yeti guy here will actually work. We'll see. It's the first time playing with this. It's the Blue Yeti Nano. Let's see. Let's see how much, because the problem is the computer is, you know, it's a lot of noise, the fan and whatnot, and I think it's just because a lot of it is a bit old, but hopefully, because I'm taking a look at the mic and the microphone sort of output here in OBS, and I lowered it in a way so that the reception, the volume, so it shouldn't catch a lot of the background noise. We will see. Now, what I'm gonna play today is sorry, there we go. Just a warning from OBS. What are we gonna do today? So we played yesterday with the you might also hear baby crying, but I guess that's normal. Yeah. So we were playing with the ifelse concept, right? And again, I kind of try to rephrase the whole thing a bit more. See, ideally I'd love to use the browser because I think there's a JS Paint, which I should probably just bookmark, you know, because I feel like there's just less things. Yeah. Let's see how that works. I mean, I don't know. I'm kind of like I have this digital pen which I used to use a lot before. And it still I think it's good, but I'm not so sure for a lot of the stuff that I'm doing might not be. Yeah, we'll see. Anyway, let's talk lesson. I know we're supposed to start at 1. Come on, just shut up. I shouldn't explain myself because I'm trying to find a schedule, and I was supposed to start at 1, but it just didn't happen this way. I blame it on the baby. Anyway, so the whole point is we have these hypergraph structures, right? So we have like nodes that represent the state of qubits, and kind of I was on the go doing a bit of tweaking to the definitions that I sort of before had, and now you kind of have. So I'm gonna run with the assumption that per state and per qubit you only have 1 node, so you cannot have 2 nodes with this for the state 0 for qubit 0, so to say, right? But you kind of have these kind of things like these, and then the idea is you have here qubit 0 and here is qubit 1, right? And so you can't. So when you apply sort of a gate like the MS gate, right? So you kind of have this definition of the MS gate. See if I can find it. Amazon probably is better. And you have this definition here, which would technically, it's like, okay, so if what happens if my qubits are in the 0 and the plus state? Then I would, in order to apply this transformation like that, then I would have to kind of first put my hypergraph in a way that I can actually just map these inputs and then turn them into outputs, right? But that means that I have to take these, make the product, right? And then say, well, I have one branch where this is 0, 0, then I have another branch where this is, 0, 1, right? So in this case, it's just 2, it's not a problem. When I have a plus here, then I have like 4 different hyper edges, and then I kind of go and I replace each. So, and I kind of run these replacement for each hyper edge, right? If I know a definition of this gate that it's more of an ifelse definition, like a conditional definition, like if qubit 0 is in the state 0, then apply these gates to the qubit 0 and 1. My assumption was that should be easier to implement, and ideally I want to make sure that I don't have to transform my hypergraph into a sort of an in-between state where I have multiple hyperedges, but I'm not sure whether there's entanglement or not. Because remember, the idea of this hypergraph model is that if there are hyperedges, the hyperedges equal entanglement, right? Because it's it's this kind of relationship between states. Like if this is in the zero state, then that other qubit is in that other state. And ideally, if I'm forced to do these, right, now I'm in sort of like a state where, you know, this is not entangled, yet I have two hyperedges. And I will have to manually kind of have a bit of a cleanup task that just goes and says, okay, like two nodes are the same, so actually, you know, this information is redundant, and so, you know, these really just transforms, it's equivalent to this hypergraph here. And I don't want to have to look for these equivalences, that's the point, because it gets complicated once you have 3 qubits, 4 qubits, n qubits, right? And so, you know, so ideally, if I know the definition, right, and we kind of worked out that the definition here was that if E was 0, G was 1, and like the definition is if Q0 is 0, then you kind of have the two branches, right, where, to be honest, I was thinking about these, and I think it's more in one of my voice notes. You apply a certain rotation to Q0, right? So if Q0 is in the zero state, then you kind of do a you do some sort of like unitary to your Q0 qubit, and then you also do another unitary, which we'll call, so this is U1 or U0, and then U1. Well, it's not a unitary in this case. You do it. You do it for Q. It's a control node actually. Yeah, that's just probably not the right way to write it, right? But your first step would be, you know, you kind of, this is just to capture this plus I, you know, here. So you would kind of do 0 plus, you know, I1, right? That stays in the 0 plus 1, and then sort of the next step is you do a control node, because then it's like, well, if it's 0, it's 0. If it's 1, then it's 1. But because the input state was 0, and then we see here that in the G case you've got the same. So this is this and that. Ah, yeah, okay, but that's yeah, but that's wrong. Okay, so I see the problem is I can't do the rotation like that, because of course it's different here, it's minus I, so it's not the same rotation, right? So it's something that I have to take okay, that's interesting. I didn't think about this before, right? So I can't do that. I can do these, right? And I can just say like, well, that's just like that, but then I need to make sure that I can put this plus I and minus I, so it looks like well, then yeah, then it's not a control node, then it's a different gate, because then what we have left is with the transformation that if it's 0, right, 0 goes to 0. So 0 goes to, I'm not so, I don't, let me just go back. So, because what we said yesterday was you have then these two kind of branches. It's the same like applying a rotation to Venice and then like a, but it doesn't have to be like, let's say we already have a mixture, right? That's just a mixture. The thing is, this mixture cannot have the coefficient, right? Because it's different, right? And now what I need to have is, in a way, the fact that so I need to get that coefficient in there in a way, right? So because I know that in this case, you know, that stays like it is, and that's just a knot, but it's not a knot, it's Because it's not the same operation. Crap. And the thing is, it just depends on these, right? Well, but that shouldn't be a problem, right? Should it? It's a 0. So eventually we want a 0, and then we want a sort of a I1, right? Also not. It's not true. It's not true. It's not true. That is not true. And yeah. So how do we go about these? Because I could try to be a bit smarter and say, no, I can't. How? So how I would go about these? What do we want to have at the end, right? Let's assume that we have a 0 here, right? So that's actually these here. So at the end I want to have. Let's try to just work it out by example. So at the end, so if I have these, and I'll just copy that here, and if I just have so that is, let's say 1. No, that is the 0 plus 1 case. Let's see, right? In the 0, 0 case, I want to end up with these. But I want general rules for the case where I just know the first one is 0. I don't know. Let's say I don't know what state is the second qubit in, right? Is it a way that I can just rule out these and say, let's say we are like that, right? And then oh god, that's complicated. And so how do we go about these? So we this is 0 plus 1, right? Or it's kind of unknown in a way, right? If this is 0, then I know that an E will be transformed into an E plus IG, whereas if it's 1, it would transform into a 1 minus IG. So in a way, like it's a like that's a construction that kind of makes sense, but I can't. Yeah, that kind of makes sense. And then it's like, well, in this particular case, like I don't. It's just a linear combination of both, right? So. Is it right for me to just kind of try to write like a transformation that says 0 goes to 0 plus I1 and 1 goes to 0 minus I1? Because that is essentially what I want to happen, right? So that is the gate that I want to ride. 1 equals so 1 equals 1 minus I0. That is what's happening here. If I ignore the first part, is it what is happening here? That this is what's basically happening? So this is my unitary. And so if I were to replace these, so this is just, well, the question is this unitary? I guess it is. I don't know. I guess I would have to double check at the matrix level. But I think if the whole thing is unitary, then the sort of the sub transformation should be also unitary. And just let's double check that works. So I've basically, I don't know if this is something that I can do, but so now if I would just plug this in here and say, well, this is 0 plus 1, so I basically have these and that. So I have like a 0 plus I1 plus 1 minus I0. And so there's going to be some interference happening here, right? And then here, in the one case, okay, that happens always regardless. So there's no, it's not that that's a condition, right? Why would it be that it's... Is it legal that I do this, so that I just say, you know, in the case this is 0, we know that always it's always 0 and 1, right? It's sort of like a 50% thing there. But then for the second cubic case, then we have these other stuff in there. But I don't know if that makes sense. If in this case you would have you have the same. I keep thinking the coffee's on the other side because then I have the microphone on the other side. Getting a bit lost though. And I'm just not, I'm omitting the normalization kind of things in here as well, the square root of 2 and stuff like that. Because what would you get? So if you have, yeah, then you get these plus these essentially, right? Well, that is it. That's because this is 0. If this is 0, then this is a transformation that's applied. I think I'm making a really basic mistake somewhere, and just in terms of how this is multiplied or whatnot, that it doesn't make me feel good. It definitely doesn't make me feel good. So if this is 0, let's think about this one. So this is 0, right? You end up with these stuff here. Which in the case is like it's gonna entangle, right? Let's dump it down a bit more, right? So let's just say we're 0. So what will be the rule, right? So say like if this is 0, like I know I have to go like E plus G, right? I know that regardless of the options, it's like E plus, so E and G, right? And let's keep the relative phase aside, or 0 and 1. So because I know that it's got to go this way, and then the transformation is still this one, right? So because it's a 0, it's a 0 plus I1. But the problem is it's not that you do that per each, is that like the end state in this case, the end state that I want to have is I want to have 0, 1, and I want to have 0 and plus I1. That is the end state that I want to have in this case, because I know it, it's in the definition, right? But if I just define this, the sort of the subunitary like these, there's just no way that there's no consistent, because I can't just like I know if it's 0, I'm gonna have something else than if it's 1, right? But that affects the whole thing. What I'm struggling is I know that the end state can be defined like that. So I know there's a definition of if the qubit 0 is in the state 0, then I know the qubit 1 is in state 0. If it's the qubit 0 is in state 1, I know that qubit 1 is in state 1 or plus I1, right? With the relative phase, this hyperspace relative phase. So I can define the end state with a sort of at the correlation level, or at the dependency level, right? But I can't but I can't find, or I can't figure out a way that I can define the operation like that. As in, like, if this qubit is this, then apply this set of operations, right? That ideally that's how a control node is defined, and that's the whole holy grail I'm after, right? Because what I want to avoid is to say if like make it as a sort of as a, if it's in the 0, 0 state, then apply this set of transformations, because that's exactly, that's already this definition, right? If it's in the 0, 0 state, then just, you know, then just do that, right? Which would be fine, but it does not, because the problem is it leaves me with something like of course in this case I know right away that it's entangled, because that's just the way that it is defined here. But if I have then like a 0 plus 1 thing here, I have to kind of break this down or expand this into different hyperedges, then apply the different rules, and then I still have to figure out if it's entangled or not. So I still have to do a different version of factoring, but I still have to do factoring. And I wanted to kind of evolve it in a way that it's the closest to, so I don't have to do actually factoring, right? Or it's an easy way, or it's just easy to do factoring or not, like, but it's even in this simple case, right? Even in this very simple case, this might definitely not be possible. I start to fear that is the way it is, right? How can I do this? Is there a way? Is there a way that I can define that in terms of like apply single qubit operations? Even if it's controlled ones, right? Because if I take a look at the sort of, let's say, let's put it this way, right? So all the gates, all the 2 qubit gates should be in a way they have like a circuit representation that is just out of the unitary gates, like the sort of the universal gates at like a C naught, like a CX, like C naught and Harvard or whatever, right? So measure in the composition, because that maybe tells me something. Like I don't know if there's a way what I can find here. Maybe in pictures I can find the gate or something. Mazurin decomposition, or gate decomposition. Or maybe something like that from Qiskit. So oh, this is it. Okay. So this is it. So this is the Mulmazer and the MS gate. I think that's it. Okay, that's pretty nuts. So it's there is control nodes, right? And that's my point. Like there's control nodes, so there's entanglement between these 2 qubits. There's entanglement between these 2 qubits, and then there's entanglement between these 2 qubits potentially, right? Because that tells me that maybe there's a way you can define it this way, right? Say, no, wait a second, but that cannot be the Mulmazuran because it's 3 qubits. I wanted to have, oh, what is the RX? Oh, a global MS gate. No, global MS gates. No, I want just the 2 Mulmazuran. So Qiskit. I just want to have the. I just want to see the decomposition. So navigating ion trap systems. The MS gate. Why is it called global? So number of qubits. Ah, okay, so in the 2 qubit case is equivalent to an XX theta interaction. An XX gate. Okay, so XX gate or RXX gate. So it's equivalent to this one. Okay. Does this load? Yeah, that's just a single 2 qubit operation. I just want to know. okay, so it was here. Okay, so this is, in theory, it's these thing, right? So that's the RXX. Okay, so that will be the Mermazoon gate. So this one here. So yeah, there's entanglement like that. Okay, now that tells me there should be a way, right? Let's just say, you know, if and so this is a U2 and this is a rotation, because maybe what this boils down to is to say, like, you know, that bit here, like the two control, the control X sandwich U1, this is in and of itself a control gate, right? So it would probably is a control U1 or something like that. So that just tells me, right, there is just a way in which you can probably you know, kind of tweak from this definition, have a tweak and say, I don't know if I'm explaining myself well, but the dependencies could be somewhere else in another basis, right? And say, if this is in the plus state, you know what I mean? Like if Q0 is in the plus state, then, you know, then do that to that operation to the Q1, to the QB1, right? Because that whole thing here, I think that whole, including the U2s at the front and at the back, like this could all be summarized as one operation. And so this kind of just basically saying, if this is in that basis, then do a control. Yeah. So it's a global MS, and that's the RXX, which is basically the MS gate in theory. Yes, and actually the strategy here is probably what I was kind of. Yeah, I think that makes sense, because look, if this is in the plus state, right, then we would have, it's a bit like you got to consider this transformation and this one here below, or not, or these and these. If I take a look at these ones here, right, where the second qubit is the same, but here is like E plus G, right? No, but then they have the. I want to take a look at. So I want to take a look maybe at the output first and see what is the condition on the first qubits, on the sort of on the input qubits, right? Because this would be basically telling me if I'm in a Bell state scenario or in a 0 plus 1 1 situation. Yeah, but that's again, that takes. Because if I would say, if I'm in the plus state, right, but then the plus state can be a combination of these and these, a combination of these and these, a combination of these and these, right? It could as well just be in all of them. Well, let's say if I'm in the plus state, I could be in these or these, right? G, which wouldn't, there's nothing that cancels out. Could be in these and these, where nothing really cancels out either. It could be in these and these, but kind of the same half. So just things just add up. But if I knew that I'm in this state, then I know that the output is it's just a it's just a NOT gate. It's basically just like 2x gates, right? If I'm in a Bell state, like EE and GG, right? So these and these, sort of thing, then essentially the transformation that I do is like an X gate on each qubit, and that's it. Isn't that sort of what's the Bell basis? Isn't that a thing? So that's the Bell basis, yeah. So that's the Bell basis, right? And I would say, so if I take these as a basis, right? If I take these as a basis, then how would the transformations look like? So, well, let's try to work this out, right? So we're taking EG and minus GA. So EG minus GA. So you would have EG and then minus GA plus IEG, right? So things wouldn't really. Yeah. So it EG minus GA. I probably have to write this down. Let's see if I can just put the whole pane aside here. Maybe here, maybe this here. And kind of say if I'm on the Bell, so if I'm on these bases, right? Like I would have EG minus GA. So if I have 0, 1, minus 1, 0, right? That's the one that I'm here, 0, minus 1, 0. Then it means that I have 0, 1, minus 1, 0. So it means that I have, then this is transformed into like a EG minus IGA minus GE plus IEG. And then kind of like these things would just basically say EG and EG, so it's like 1 plus I times EG, and then minus 1 plus I times GA. So sorry, this is 0, 1, 1, 0, right? So all that I have to do is apply. So the point is I get it expressed in the same, like you see, because these things don't change. If it's EGGA, EGGE, right? The whole thing is GEGGE. So I have the same two types of base elements, right? And the only thing that then at the end of the day changes is that you kind of have different weights here, different amplitudes. So the operations, so this would be literally then a whatever gate that does this rotation for this particular state, and that's it. Yeah, is it? I don't know. Yeah, well, that's a global. The thing is, that is a global phase. Actually, there's nothing. That is just, these two things go out. It's just a global phase. Like you can just ignore that. And so this means that in this case, you do nothing, really. In the case 0, 1 plus 1, 0, it's sort of the same story. And then in the case 0, 0 minus 1, 1, 1, wouldn't it be the same story? But again, you know, what's the point, right? Because then that doesn't help me either, because I would then have to say, so what is 0? What is 0 from a Bell state perspective? I would still have to do the whole decomposition of 4 elements. That just makes no sense. It just doesn't help me. I think it doesn't. This definitely doesn't help me. This definitely doesn't help me. I hope you see what I'm getting. It's just I guess maybe without getting more formal, it's going to be difficult to figure out. But it's and that's the part that I'm always scared of. And there's no clean way to say if the first qubit is 0, then what do I do to the second qubit so that it actually runs a Murnau-Zurn, right? So, and we can have different examples. So if I've got a 0, then I just have to apply this transformation. Whereas if I got a 1, then I have to apply, like I know that I have to go like 0, 0, 1, so I have to create 2 hyperedges, right? Because that's what it's telling me. But then in this case, yeah, but why wouldn't I be able to define it like that and to say that why I can't say it like that? So under these branch, I apply. Who the fuck is this guy? Can I just ban this person from here or something? I'll ban. Someone just promoting something in the chat. That's not cool, man. How are I going with time? Okay. Because then, as I said, like then I kind of have these 2 different sub rules, right? So this goes to 0 plus I1, and then this goes to 1 minus I0. So that as a sort of sub rules, right? So the G here stays G and G. Yeah, but that's nothing else than just running these, right? Just saying, well, I know this is these, so I just kind of make these 2 branches, like, and that's it, and we're done. The problem is, how do I do it in a way where if here I actually have a plus state, right? If I have a plus state, I want to know what is the operation that I've got to do. And if I have a plus state, like a 0 plus 1 state, you know, what's the operation that I have to do? Like, do I have to do these 2 operations? I thought I had it. I thought I kind of had it, but it's not really looking good. I know that if it's 0, I just have to focus on these two rules. And let's say I don't have the knowledge about the second qubit, right? So what is the operation that I have to do so that this is then correct? That would be the question, right? I know that then what I know is that the value of the second qubit depends on both. It does depend on both the first and the second, does it, or not? It's why? Because like after the fact of having just transformed the thing, right? Let's say let's say that I just don't know about this state, right? But I know that I know that. So the question that the first question I have to ask myself is, like, is this gonna tell me about this state or not, right? Like if I measure this to be in a G state, then then I can either be, then it just can either be that this is 0 or this is plus IG, right? Maybe that's what I have to do. Maybe the way you construct this is just saying, look, let's put the things on the table, right? So it could be 0, like the outcomes, right? Like it could be that you have a 0, 1 or 0, 1. You don't know, right? Like you you really don't know. But if we know something about our input, and ideally I just want to know the state of one of the qubits, because that's the point, right? To define that. If I know that state, I know I can concentrate on these two rules. This means I just don't focus on these ones here. So then I know that I have this configuration here, and that actually, okay, so what does 0 tell me? So if it's 0, if it's E, then I'm either I'm here. Oh, that might work actually. I'm either like here with the minus I kind of, you know, coefficient, because this is here, right? Or I'm here. Look at these. That is good. That is good. That doesn't look, that's good. Because that's what I'm looking for. I'm looking for a way that I can that I can't really define that entanglement without, like, I want to be able to make a transformation with replacement, with replacement rules without me having to do some sort of factorization after the fact to check whether it's like this or not, right? But I'm not so sure this is going to take me anywhere, right? Let's see. Now, if I know that this is a 0, does this match? What else do I have? So if this is a 0, I'm either in here, which I have it, or in EG, right? So here, right? Yeah, okay, and I guess that makes sense. And so if this is G, I'm either here or here. Okay, so that reflects, but like that's plus I. So that's kind of cool. That's kind of okay. So that reflects the sort of entanglement situation, right? But how does this help me? So I know that I can create this structure if this is that, but then, you know, the truth is I do know this state, right? Let's say that is 0 plus 1. What does this tell me? Well, for a fact, like for starter, if I know that this is a 0, right, then I know I can get rid of these. Then I know I can get rid of these. Then I know I can. This structure, right? Then I know I can. Then I know I can get. Yeah, if I know that it's 0 plus 1, then I know that I have to keep this structure because I don't know where I am. It could be here, it could be there. Maybe that's the trick, right? Maybe that's the trick, is that the situation here would basically tell me which rules I can select and then kind of create that structure. But still, that means yeah, but it's still I have to do something after the fact. You know what I mean? Like, that's the problem. I still have to do some sort of after the fact kind of thing where, because is there entanglement here? Is there entanglement here? Like, that's the point. Damn it. That's what I'm trying to figure out all the time, because basically with 3 qubits it's just going to be like, it's just a factoring, right? So I don't want to have to do factoring. But that seems to be right, because it seems to be there's no entanglement. It seems to be there's no entanglement. Or wait, is there? Because of these damn coefficients. So yeah, but it's like, if I am here, I could as just well be here or there. If I'm here, I could just well, you know, there's no entanglement, just because there's just no entanglement because I can be in both places. Like, there's no. But isn't that factorization then as simple as saying that if I have qubits, if I have sort of qubits that belong to like two hyper edges, those, then it just then it just means that that's not the thing, or what? Does this map to 3 qubits as well? Because that could just be an easier thing to do. That I define these values, and then I just define the possible hyper edges based on how this based on what I know from the input, right? If I know from the input that I'm in a 0-0 state, then I will just I'll just draw these two, and then I know this is entangled because it's only each node belongs to just one or to less than 2 hyper edges, and in this case, you know, because it's just a 2-level system. That's kind of what it is. The problem is, once we go to a 3rd qubit, things can get tricky, because you can have 2, but then it's still they can be with different qubits, right? So in which case I don't know how to deal with this, but maybe this is maybe that's just the way to go. I don't know. I have the feeling that I'm just giving rounds to this thing without really knowing what I'm doing well or not. Like, because because that doesn't tell me anything about the operation. But I'm just kind of applying these again. I'm like going back to my original. It's just a different encoding. Because before I used to do like, right, and then of course they are all like these, and each kind of has, so they're all connected, and then each has their own thing, and blah blah blah. And then but then you kind of like, okay, so this is zero. Should we merge the hyperedges or not? Like, and this was just like complicated. This was complicated to deal with. But now here I can, and I think I played with that as well, but I'm not so sure. So now I have just one node representing the 0, and then I could kind of count the hyperedges and whatnot, but it doesn't help me. I feel that doesn't help me. You know, in a way. So if I know that I'm in the E case, that I know that I have to, that this is 0, then I know I have to draw these hyperedges and these hyperedges. Yeah, and then it depends on what state I'm in. I know what I have to draw all of them, or I just have to draw these, or I just have to draw these, for example. Right? So I know what the hyperedges to draw. Because then that wouldn't be entangled. Like if this is 0 plus 1, that wouldn't be entangled. You just kind of have 0 minus I1 as a sort of a state here, and then here is 0. Well, I don't know, to be honest. Yeah. I don't know. Didn't really move much forward. I just have to keep thinking about this. Anyway, see you next time. I'll try to do actually a bit more hands-on on Friday. Kind of code maybe this idea and kind of work a bit with code and see where we take this. Yeah, I kind of like swinging between quantum mechanics and a bit of the details of these. It's everything around entanglement, but it just, I still would like to have that notion of like, can I define an operation as a sort of an ifelse kind of thing, which I fear you can't generally. Maybe there's some cases where, I mean, there's definitely some cases where you can, right? Like a control not, right? But it's like, you know, if then do that, like, if I know this is a 0, like, is there an operation that I can, is there a set of operations that I can do on the top, on both qubits, right? That will lead to the right state, right? Not knowing what's in here. So that will kind of be that's kind of the question. It just feels like there should be. Anyway, stay tuned for the next one on Friday, and have a good day and a good week. Bye.